This video will be on angular motion, so I'll be talking about angular velocity, angular acceleration, tangential velocity and tangential acceleration. Now, because we're looking at motion in a circle rather than in a straight line, then we might think that we could take our measurements in degrees, but measuring in degrees doesn't really tell us how far we've travelled, which is why we use radians instead. In the diagram here for 1 radian, the length of the arc here is radius r. The length of the arc is proportional to the angle that is swept through, and we call that angle theta, which represents our angular displacement, which I'll talk about later. It makes sense to define the angular displacement as the ratio of the arc length, which we'll call s here, to the radius. So to write that in the form of an equation, the angle is equal to the arc length s divided by the radius r. If we consider the arc length to be the circumference of course being 2 pi r, then our expression becomes 2 pi r divided by r. The r's of course will cancel there, which is going to give us an expression of 2 pi. So what that means here is that 360 degrees is equal to 2 pi radians. So we've already mentioned that the angle theta is what we call the angular displacement. We can think of that much in the same way as we think of linear displacement in a straight line. So if we take 2 points, point A and point B, then the displacement is how far we have gone from our starting position. So the arrow there would indicate S. We can take a similar approach to angular displacement here. It's really a measure of the angle that has been swept through from the starting position. So if this is our starting position here, our starting position A is here, then the angle swept through is whatever angle we have travelled through as we cover this particular arc length. So that's what I mean by the angle that's been swept through or travelled through from some starting position. The angular velocity is a measure of the angle that is swept out per second. So if we think about that in terms of linear speed, we would think about the distance travelled per second. Here it's the angle swept out per second. And that's equivalent to the rate of change of angular displacement with respect to time. The symbol for angular velocity is omega, which is a sort of curvy looking W. So if that's equal to the rate of change of angular displacement, then we can write that as d theta. With respect to time gives us dt. And the units for omega are radians per second. So that's where the radians come in from the first slide. Notice that I'm writing radians as RAD and not RADS. Radians are rad. I try to remember it as rad as in radical. So radians are rad. That's the correct unit there. That's a common mistake. So this means then that any displacements must be converted to radians before being used in this particular equation. For example, if you've got, say, 6 complete revolutions, so that could be 6 revolutions of a turntable, 6 revolutions of some scary theme park ride that goes in a circle. 6 complete revolutions, 1 revolution is 2 pi, so that means that in radians that would be 6 multiplied by 2 pi. Would give you your value in radian there. Just as linear acceleration is defined as the rate of change of linear velocity with respect to time, The angular acceleration is the rate of change of angular velocity with respect to time. So we'd indicate that as d omega by dt. And angular acceleration has the symbol alpha. So our expression for angular acceleration would be alpha is equal to d omega by dt. Alpha is measured in radians per second squared. So just like linear acceleration is meters per second squared and linear velocity is meters per second, here angular velocity is radians per second and angular acceleration is radians per second squared. So if we go back to looking at a similar image to some of the ones we've shown in the earlier slides, where we've got some sort of angle that's been swept through, some sort of arc length s, our angular displacement theta. If we imagine that at this point here we have some kind of angular velocity that's omega naught, so like an initial velocity, initial angular velocity. This is our final angular velocity, omega. Then just as we would do a equals v minus u over t for acceleration in a straight line, here we can use alpha being equal to omega minus omega naught divided by t. So this relates back to the initial equation on this slide, but just looks at it in perhaps a slightly simpler way, and one that relates very nicely to an equation that we're very familiar with, which is a equals v minus u over t. Although rotational quantities are important, it's also useful to consider what we call tangential qualities too. So the rotational velocity of an object here is obvious. You know, that's the speed that it is rotating at, or the velocity it's rotating at. But there's also a velocity that acts at a tangent to the circle. You can see that in the diagram here, which is denoted by v. The tangential speed is measured in meters per second because it's in a straight line. You can think of that in terms of satellite motion. So there is an angular velocity that is associated with the movement of the satellite, but at any point in time there is a velocity that acts in a straight line, and that is the constant velocity of the satellite as it moves around the Earth. To go back to the diagram here, the arc length s, which remember is the length here that we're kind of sweeping through on the outside. The arc length s is equal to r times theta. That's just a rearrangement of the equation from the first slide, so go back to that if you're not sure of where that comes from. So that becomes d, if we're thinking about things in terms of linear quantities. D is equal to r times theta. So if we take into account v equals d over t, speed equals distance over time, then we get v is equal to r theta divided by t. We already know that theta over t is omega, so therefore we can say that v is equal to r times omega, meaning that the tangential velocity, v, in meters per second, is directly proportional to the angular velocity, omega, in radians per second. Applying a similar logic to angular velocity, we can find another way to calculate the angular velocity using omega equals 2 pi over t. The period t is the time for one revolution, and in one revolution there are 2 pi radians, so it's just exactly like v equals d over t again. If that tangential velocity is changing, so if this is v1 and this is v2, and v2 is somehow different from v1, then that means that there is also a tangential acceleration. So I'll indicate that with at. So there's a tangential acceleration in a straight line at a tangent to the circle. The tangential acceleration is measured in meters per second squared. We're going to take a equals v minus u over t as our starting point again. We've already figured out that v is equal to r times omega, so we can substitute in for r times omega, where omega is our final speed that will occur at this point. Our initial angular velocity occurring at this point will be omega naught, so we can say minus r times omega naught divided by t. So then a is r multiplied by omega minus omega naught, taking out a common factor of r there, divided by t. Omega minus omega naught, as we saw in one of the earlier slides, this whole term here becomes alpha. So a is equal to r multiplied by alpha. This again shows the dependency of the tangential quantities on the rotational ones. An increase in angular acceleration will cause an increase in tangential acceleration. To summarize the terms that we have, the angle that's being swept through in a particular period of time is what we call the angular velocity omega. If that value is changing, so if we start off here with a value omega naught and finish at a value omega, and there is a difference between those, then that means that we also have an angular acceleration, which we call alpha. In addition to these angular values, there are quantities that are taking place at a tangent to the circle. So this value v here is the tangential velocity. If we have some changing velocity between v1 and v2, then that means that at a tangent to the circle there, we have what we call a tangential acceleration. So there are four quantities there, but they're quite easily mixed up. So it's important to make sure that you understand fully the differences between angular motion and tangential motion. And to bring all the equations together, angular velocity omega is equal to the rate of change of angular displacement with respect to time, d theta by dt, sometimes written as theta divided by t. Angular acceleration, the symbol alpha, is the rate of change of angular velocity with respect to time, so that's d omega by dt. Remember, sometimes written as omega minus omega naught divided by t, which is really just the angular equivalent of a equals v minus u over t. Tangential velocity we've shown is dependent upon angular velocity, v equals r times omega. Tangential acceleration, a, also dependent on angular acceleration, a is equal to r alpha. In terms of units there, this is angular, so this is in radians per second. Angular acceleration, radians per second squared, meters per second for tangential velocity because it's in a straight line, and meters per second squared for tangential acceleration. Some other equations of note here that we've discussed, S equals R alpha can sometimes be useful, as can omega equals 2 pi over t, if you're given the period, say, and you wanted to calculate the angular velocity. A couple of pieces of homework from what I've just been through there. I'd like you to make a list of the linear quantities. So I'm talking about suvat there really. So you would list suvat, list the units, then begin to list the quantities for angular motion and their corresponding units, just so you can see how the linear and the angular quantities relate to one another. That can sometimes be quite useful to do. The second piece of homework here is to see if you can use integration to derive the three angular equations of motion. You'll be able to use a similar method to that which we used with the linear equations of motion. To give you a wee bit of a help with that, your first equation that you're looking to derive will be omega equals omega naught plus alpha t. So see if you can use the knowledge in the video coupled with the techniques that we used for deriving the linear equations of motion to give me 3 equations for angular motion.